Right now we're watching 20,000 games played by an AI as it explores the world of Pokemon Red. In the beginning, it starts with no knowledge whatsoever and is only capable of pressing random buttons. But throughout 5 years of simulated game time, it gains many capabilities by learning from its experiences. Eventually the AI is able to catch Pokemon, evolve them, and defeat a gym leader. At one point it even manages to exploit the game's random number generator. But perhaps more fascinating than its successes are the ways that it fails, which are surprisingly relatable to our own human experiences. It turns out that studying the behavior of an algorithm can actually teach us a lot about ourselves. In this video, I'll tell the story of this AI's development and analyze the strategies it learns. At the end, I'll go deeper into some technical details and show you how to download and run the program yourself. Let's start by asking, how does it work? The AI interacts with the game much like a human. It takes in images from the screen and chooses which buttons to press. It optimizes its choices using something called reinforcement learning. With this method, we don't have to tell the AI explicitly which buttons to press. We only need to give it high-level feedback on how well it's playing the game. What this means is that if we assign rewards to the objectives we want it to complete, the AI can learn on its own through trial and error. So what does this look like? The AI will start with no knowledge or skills whatsoever and will only be able to press random buttons. So for it to get any useful feedback, we need to create a gentle curriculum of rewards which will guide it towards learning the difficult objectives. Perhaps the most basic objective to start with is exploring the map. We'd like a way to reward the AI when it reaches new locations. More generally, we'd like to encourage curiosity. One way to do this is by keeping a record of every screen the AI has seen. As the game is being played, we can compare the current screen against all screens in the record to see if there are any close matches. If no matches are found, this means the AI has discovered something new, so it will give it a reward and add the new screen to the record. Rewarding it for unique screens should encourage it to find new parts of the game and seek out novelty. Alright, now that we have an objective, let's start the learning process and see how it goes. At this stage, the AI is essentially pressing random buttons just to see what happens. To gather experience more quickly, we'll have it play 40 games simultaneously and each will play for 2 hours. Now the AI will review all of the games and update itself based on the rewards it earned. If it goes well, we should see incremental improvement and the whole process can repeat. After a few iterations of training, the AI finds its way out of the starting room noticeably faster than when its behavior was random. For some reason though, instead of exploring Route 1, it becomes fixated on a particular area of Pallet Town. Why is this? It turns out, when you're seeking novelty, it's easy to become distracted. Notably, the area it's stuck in has animated water, grass, and NPCs walking around. It turns out this animation is actually enough to trigger the novelty reward many times. So according to our own objective, just hanging out and admiring the scenery is more rewarding than exploring the rest of the world. This is a paradox that we encounter in real life. Curiosity leads us to our most important discoveries, but at the same time, it makes us vulnerable to distractions and gets us into trouble. As humans, we can reflect on our own sources of intrinsic motivation, but we can't easily change them. In contrast, it's straightforward for us to change these for the AI. Returning to our current scenario, a reward is triggered if more than just a few pixels differ from previously seen screens. But if we raise this threshold to several hundred pixels, the animations won't be enough to trigger the reward anymore. This means the AI will no longer get any satisfaction from watching them and will only develop an interest for more novel locations. Note that each time we modify the rewards, we restart the AI's learning from scratch because we want the full process to be reproducible. After this change, the AI starts to explore Route 1. Eventually, it makes its way up to Viridian City. This is great progress, but now there's another problem. In most battles, the screen looks pretty much the same, so there's not much exploration reward to be gained doing battles. This in turn causes the AI to simply run away from them. But ultimately, it can't progress without battling. So to address this, let's add additional rewards based on the combined levels of all of its Pokemon. Now with this new incentive to gain levels, the AI gradually starts winning battles, catching Pokemon, and leveling them up. Eventually, its Pokemon reach a high enough level that they start to evolve. It actually tends to cancel the evolutions at first, before finally deciding that it's beneficial. It does, however, seem to get stuck when a Pokemon battles long enough for its default move to be depleted. Despite this, after many more training iterations, by version 45, there's substantial improvement. At this point, we now see a Pidgeotto being evolved for the first time, and it's also finally figured out what to do when a move becomes depleted, and is able to switch to an alternative one. This will turn out to be super important for something that happens later on. At version 60, the AI starts entering Viridian Forest and begins its first trainer battles. By this point, it actually has enough experience that it succeeds on its very first encounter. After this, it slowly starts figuring out how to navigate the forest. Finally, at version 65, it's found out how to get through the forest and makes its way up to Pewter City. But something still wasn't right. Despite making a lot of progress, the AI is charging straight into battles, even ones it's not able to win. To make things worse, it never visits a Pokemon Center to heal, which means that when it loses, it's taken all the way back to the very beginning of the game. We can try to fix this by subtracting reward when it loses a battle, but this doesn't work quite like we would hope. Instead of avoiding difficult battles, when it's about to lose, the AI simply refuses to press the button to continue, stalling indefinitely. This technically satisfies the objective, but isn't what we intended. While studying the effects of this, however, we noticed that on very rare occasions, there's something else subtracting a huge amount of reward. Just once per training run, there's consistently a single game where a reward 10 times larger than anything we intended is deducted. Replaying the moment just before this happens, we see the AI walking into a Pokemon Center and wandering up to a computer in the corner. After logging in and aimlessly pressing buttons for a while, it deposits a Pokemon into the system, and immediately a huge amount of reward is lost. This is because reward is assigned as the sum of the Pokemon's levels, so depositing a level 13 Pokemon is losing 13 levels instantly. This sends such a strong negative signal that it actually causes something like a traumatic experience for the AI. It doesn't have emotions like a human does, but a single event with an extreme reward value can still leave a lasting impact on its behavior. In this case, losing its Pokemon only one time is enough to form a negative association with the whole Pokemon Center, and the AI will avoid it entirely in all future games. The root cause is that we never accounted for the unexpected scenario where the total levels can decrease. To address this, we'll modify the reward function so that it only gives any reward when the levels increase. This seems to fix the issue. After restarting the training, the AI starts making visits to the Pokemon Center. Finally, we see it starting to challenge Brock in the pewter gym. This battle is much harder than the other ones and poses a significant challenge because the AI's previous experience is now working against it. Up to this point, it's had great success using just the primary moves and has learned to rely on them exclusively. Now, it needs to use something else. This issue might seem trivial, but even humans struggle with the same fundamental problem. Our experience and biases help us make decisions and solve problems more quickly, but they also limit our thinking and hamper our ability to approach a problem from a new angle. To make matters even worse, if the AI loses the battle too many times, it will actually learn to avoid it altogether. But after carefully tuning our rewards and countless failed attempts, the AI finally has a stroke of luck. In one of the games, we see it starting the gym battle with just one usable Pokemon that has only a fraction of its hit points and available moves. Normally, this would be a pretty terrible strategy. It doesn't know that a water-type move will be super effective against the rock Pokemon. But because Tackle is fully depleted, it sees it needs to use an alternative move and switches to Bubble instead. And finally, after over 300 days of simulated playtime and 100 iterations of learning, the AI defeats Brock for the first time. This accidental breakthrough helps it learn to choose Bubble as its default move, and in future games it wins this battle more consistently. This honestly exceeds my expectations of what I thought would be possible when I started this project. It did take a huge number of experiments to get here, but I still felt amazed each time I checked in on a training run and discovered that the AI had reached a new area. I would go as far as to say it was a very rewarding experience. So this seems like a reasonable stopping point, but just out of curiosity, let's see how far the AI will go if we let it continue. After the gym battle, it starts encountering trainers in Route 3. Eventually, it reaches the entrance of Mount Moon. Inside the Pokemon Center here, a man will sell you a Magikarp for $500. Magikarp isn't helpful at all in the short term, so you might expect that the AI won't be interested in it. However, buying it is a super easy way to gain 5 levels, so the AI buys it every time. Over all of the games, it buys a total of over 10,000 Magikarps. The AI's behavior might seem silly when its objective has become misaligned from its intended purpose, but there are times when the same thing happens to humans. In order for the AI to progress in the game, we configured it to find ways to increase its levels. Similarly, evolution has selected humans for survival as hunters and gatherers, which naturally configured us to find ways to acquire scarce foods. When the AI reaches an area with a cheap but pointless Magikarp, it buys the Pokemon every time because this increases its total levels. And as humans have reached our modern age of abundance, we instinctively buy unhealthy foods because they contain the historically scarce nutrients. Each of these proxy objectives arose from very different circumstances, but when their environments changed, they both became misaligned and no longer supported their original objectives. Next, the AI starts to explore the cave inside Mount Moon. Up to this point, it's fought every wild Pokemon that it's encountered. But Magikarp is so ineffective that it eventually learns a special behavior just for this Pokemon. If Magikarp is sent into battle in any situation, it will try to run away no matter what, sometimes even while fighting a trainer. despite exploring a lot of the caves, it seems to get stuck in this passage, possibly because the area is too visually uniform to trigger the exploration reward. If we extend the games to run longer than 2 hours, it's able to evolve Blastoise and Pidgeot, but it never makes it all the way through Mount Moon. We could keep trying to improve our reward function, but instead, we're going to use this as a stopping point and start to analyze what the AI has learned. This visualization shows how the AI navigates around the map. Each arrow indicates the average direction that it moved while standing on that particular spot. One fascinating pattern is that it seems to prefer to walk counterclockwise on almost all edges of the map. This means that when standing with an edge to the right, it prefers to walk up, which is shown in blue. When there's an edge above it, it prefers to walk left, shown in pink. When there's an edge to the left, it prefers to walk down, shown in orange. And when there's an edge below it, it prefers to walk right, shown in green. It's hard to know for sure why it developed this behavior. One explanation is that this heuristic helps it navigate with limited memory and planning. If you walk around the perimeter of a two-dimensional space, you're guaranteed to pass all entry and exit points. So by picking a direction and following an edge, you can reach all possible junctions. The AI doesn't always follow this pattern, but it does seem to help it recover after it gets off track. However, there are locations where its navigation fails and the AI becomes physically stuck. For example, at the bottom of Route 22, there's a long area with nothing useful. The one-way ledge on the top means that there are many ways to enter the area, but there's only one spot where it's possible to leave. This acts like a fly trap, and the AI's stochastic movement causes it to get stuck and spend a disproportionate amount of time here. We can also visualize how the AI's behavior changed over the course of its training. Here the early training iterations are shown in blue, the middle training iterations are shown in green, and the later iterations are shown in red. Here we can clearly see that in the middle of its training, the AI was taking one path through Viridian Forest, but later it switched to a different one. Another interesting behavior, which developed partway through the training, happens in the first few moments of the game. For some reason, it was starting every game with the exact same sequence of button presses. This was confusing, particularly because the movement didn't even follow an optimal path. Watching a little further, however, something interesting happens. It throws a Pokeball immediately on its first encounter and succeeds on the first try. What this made me realize is that even though the game contains many randomized elements, it still behaves deterministically with respect to the player's input. This is something well known to speedrunners, and it seems that the AI has taken advantage of the fact that it starts from the same state in every game to reliably catch a Pokemon on its very first try. We also can visualize other statistics to understand what happened in all of the games that the AI played. On the left, we can see every Pokemon that the AI caught at least once. On the right, we can see at what point in training those Pokemon were caught. The height of each region is scaled logarithmically, so the Pokemon that represent the thicker regions were caught thousands of times, whereas the Pokemon representing the thinner regions may have only been caught a handful of times. Reflecting on all this, it's incredible that relatable experiences can emerge from an algorithm playing a video game. So much has happened during these tens of thousands of hours. There simply isn't enough time to discover all the interesting stories, much less document them. So here we conclude the main part of the video. In this next section, we'll dive into some technical details, explore strategies for running experiments efficiently, consider future improvements, and go over how to run this program yourself.